welcome all to the first distinguished lecture in the Columbia Engineering lecture series on AI, and also the last day of Climate Week of Columbia Engineering. And we are very fortunate to have Pierre Jeantin give the inaugural lecture today. First we'll start with a land acknowledgement that, this is Lenape land. And I just wanted to run you through what the schedule is. So hopefully everyone's registered and is here. Pierre is going to give his talk now. And after the talk, there's a reception and networking session right next door in Carlton Lounge. So please do join us for the reception. And now to introduce Pierre, or give the opening remarks, I'll ask Dean Shifu Chang to come.
All right, good afternoon, everyone. Really good to see so many friends and partners, our faculty and students here. Friday seems to be a more convenient day for most people to come to attend this wonderful event. So as Michelle mentioned, this is the whole week of the celebration and also collaboration to celebrate this Climate Week, NYC, right, citywide. Some of you maybe attend other activity around the city. This week we have many seminars and events on different topics, right, on nuclear plasma fusion, on green energy efficient computing with IBM, with air pollution modeling, and also with sustainability, sea level rising, terrible hurricane in Florida. This is just such an important topic, right? How do we increase the resilience for the environment and the built environment here? And so talking about all these climate challenges, now is the time to really focus on climate actions. And engineering, as we all know, we have a responsibility and also opportunity to play an important role here to provide solution. And this is done through the collaboration with many partners, including our sister schools from other schools here, Data Science Institute, Climate School, Business School, Policy School, everywhere, as well as our partners from government, from industry around the whole world here. Now, as Michelle mentioned, today we are very excited to launch. This is the first lecture of this series. Getting more air here. I think air ventilation of the building is an important topic for climate problem too, right? We have some faculty working on how to manage the workflow and environment in the building also. So this lecture series is really very important for the strategic action of the school, as well as a university-wide AI initiative. I myself, with Michelle, with Jeanette, with Guru, has been asked to lead this university-wide AI initiative. And one of the unique strengths of Columbia, or our aspiration, is really leverage our strengths across these disciplines. Columbia has 17 schools cut across every knowledge discipline that we can explore and we can leverage to help to contribute a solution. The other unique aspect is our deep bench of knowledge expertise and our really leading expert in this area, particularly in AI and computational science. If you count our faculty in different departments, more than 70 or 80 faculty members working directly or indirectly in the AI area. This past year, we hired close to 10 faculty members in AI area across different departments. Many of them in computer science, in electrical engineering, mechanical engineering, IEOR department, biomedical engineering, and many other areas. And as a result, we have been able to leverage the strengths across the school to develop the partnership in different areas, specifically a research center. And one of the research center led by today's speaker, Pierre Jeantin, is called LEAP, L-E-A-P, right? Learning from the Earth and Physics and AI. And that's what he is going to enlighten us, how AI and a lot of emerging massive amount of data from climate can be harnessed to improve this long-term projection accuracy, reliability of the climate model. And having this accuracy of a long-term projection is so important for us to plan in the long term strategy, how to adapt to this extreme weather change or environmental impact because of the extreme incident and natural disaster. The other aspect we have taken very intentionally is provide a support infrastructure. And so we create a very important position called Vice Dean for Computing and AI. So we are very lucky to have Vishal Misra to lead this important position. He is a very well-known, renowned computer scientist, very active pioneer AI researchers. Some of you may be receiving his email on how generative AI ChatGPT tool can be used to enhance classroom learning, tutoring, coursework planning, as well as advising and many, many other things. So I think with those efforts, hopefully we as a school can actually make more contribution in this important area. So with that, I'll invite Vishal to introduce our speaker today.
Thanks, Shifu. So, I was here on Monday, also doing a session on sustainable computing and AI, and how AI might affect the climate by sort of the amount of energy that's used in data centers. So that was kind of sort of the negative part of AI. But today I think Pierre is going to tell us about how AI can be used positively where climate is concerned. So, both AI and climate are hot topics, pun intended. But we are very fortunate to have Pierre Gentil here. So Pierre is the Maurice Ewing and J. Lamar Roselle Professor of Geophysics in the Department of Earth and Environmental Engineering and Earth and Environmental Sciences. He got his bachelor's from Supero in France, and then PhD from MIT in 2010. And as Shifu mentioned, he's the director of LEAP, our Center on Climate and AI. So with that, Pierre, thank you.
So thanks. It's exciting to be here today, especially at the end of Climate Week. It was really impressive to witness how New York City has really become almost a capital for climate and climate research, and also interest. We're seeing also a lot of investment potentially in that field. And today I wanted to maybe close and link that back to computational science and thinking about some of the excitements that we've been witnessing, especially myself, but also some of the challenges that we're witnessing now, and what are some potential directions moving forward, and especially some of the excitement around generative AI, and I'll show you some of that at the end. I'd like to acknowledge some slides and some background information I'm going to show from Stefan Hoyer, leading research at Google on computational science, doing a lot on climate as well, and Jon Hefner from Pasteur Labs as well, also doing very innovative type work on differentiable modeling. So I call that talk Futures, because I don't know the future yet, as no one does, I hope, of computational science and climate simulation. I'll try to make a parallel between some of the lessons we learned from climate, which is kind of a complicated computational science problem, and how we can potentially leverage that, and we can use some of what we've learned to other fields as well. And what I'd like to do is trying to learn from the AI revolution, right? We tend to think about the everyday use of AI, but what were some of the pillars of this AI revolution? So I'll try to walk you through some of that. So just to orient yourself, very quickly, I'll get into some of the progress that we've made using climate and on climate modeling using AI, but also some of the challenges that we are witnessing right now and some of the boundaries that we are seeing. And then trying to, again, do a leverage and trying to learn from the AI revolution, and what are really the drivers and the pillars of this AI revolution, and how can we potentially transfer some of that to computational sciences as a whole. And I'll try to put a vision, and we just had a paper published actually 2 days ago, thinking about this vision for the next generation of climate models and potentially computational tools as a whole, very much leveraging the AI revolution. And I'll end up with generative AI and how generative AI most likely is going to be central to that potential vision. So just to step back a little, so what's the gap we're trying to fill? We are really looking, in our particular case at LEAP, we're interested in climate adaptation and trying to think about how can we really think about extreme events, right? Every year now we are witnessing more and more extreme events, flooding, so there's one going on right now in Florida, drought events, heat waves, or even new types of events like the wildfire event that we had last year and the smoke that we got, right? So it's not just like the past, but we need to see what's coming up next, and a lot of that we haven't seen, right? So there's a lot of extrapolation and things that are way beyond just training data we've had in the past. But for adaptation, we need kind of two components, I would say. The first one is accurate information and really what we call a projection about the future. And for that, we typically use physically based model, and we are going to see if potentially we can go beyond that. But we typically use a physically based models where we have equations, and we use that to predict or what we call project the future. And then the second piece, and we had a great meeting actually today with AWS, is thinking about how can you make that data accessible to a broad range of stakeholders, right? So this is an example here where we've created this data viewer. You have a cloud-based infrastructure, and you can really poke and interact with the data. And we are trying to go a lot further now with AWS and that particular partnership. So if you're interested, I'm happy to talk to you about that and communication, but that's not going to be the central theme of that talk. So for today's talk, we are going to talk more about modeling and computational science. And kind of the unfortunate truth here is that when we look at climate models, they tend to be actually very uncertain. And what I mean by that is that we tend to have many, many different climate models coming from many modeling centers across the globe, typically associated with different countries. And when you look at them and you look at the different projections that they give you, whether for temperature or precipitation or whatever you're interested in, they give you a wide range of answers, right? Of course, they tell you that the planet is warming. There's no doubt about that. But if you look, this is just an example here looking at the past in blue and then looking at those different projections. The different colors are based on different scenarios of emissions. So this is more like socioeconomic type behavior. But even if you control for that up to 2050, you can see that there's a huge amount of spread in terms of how those models are actually projecting the future. And this is problematic because this is here a very aggregated metric, which is used for the Paris Agreement. Actually, what we do is we take the average across those, but it's most likely not true. There might be better models than others. We just take a democratic vote here. And that's used for policy making, such as the Paris Agreement, but that can be also used at a local level to think about infrastructure planning or adaptation at a local level. And this is not just at the global scale, but if you look now, this is an example here at a regional scale over the US, and that's a slightly more complicated plot, but looking at what we call precipitation distribution. So those are more intense precipitation to the right, and basically their frequency that you can see here on the y-axis. And when we look at a typical climate model, which is here in green, you are basically missing a lot of the extremes. So the black line are observations from rain gauges. And then you can see in red, this is a model that's at a much higher resolution, at a kilometer scale resolution. That green model is at 100 kilometer scale resolution, which is the standard that we use now for climate models because they are very computationally expensive. And the main point being that we miss things that we are really interested in, like extreme events, extreme rainfall, flooding events. We just won't have that in those models, or we won't have that to the magnitude that we need. And that's highly problematic because that's what you need to drive a lot of the risk assessment and physical risk of society. So that's something we need to solve. It's not just for physical risk. You can also think about the biogeochemical cycle and the carbon cycle, and that's actually important to think about mitigation purposes, right? When you think about those different models, this is the amount of carbon that they will be uptaking by 2100. So the higher it is, the more uptake you will have from the land and from the ocean. And you can again see a huge spread, and when you're below the zero line here, it means that the land will act as a source, so it's going to be adding carbon dioxide to the atmosphere as opposed to picking up a lot of carbon dioxide. And to give you a sense, the land now is picking up roughly 1/3 of the emissions. So when we are emitting, say, with our car, 1/3 of that is going to be picked up by the land. So they are doing a great favor to humanity, right? They are taking a lot of that back into the system. So that's going to be defining also the trajectory of climate, and so we need to nail that down. And again, for that, we use climate models, and we need to represent those processes correctly. And that's a huge challenge when you look at just the diversity at the zoo of response that you're getting there. So why is that? So why do we have all of those issues? And the main reason is that it's complex, right? The Earth is a very complex system. You have to deal with clouds, with turbulence, a lot of biogeochemical processes. And again, to give you a quick sense, this is a typical grid size of a climate model, which is, you could think of that a very pixelated view of the world. If you were born like me a few decades ago, it would be like the old video games, right? Where it would be a very coarse-scale version of the world, a very, very pixelated view of the world. And what it means is that you cannot really resolve those clouds, right? You cannot directly represent them, and you need to actually make up for them in some sort of empirical way. And that empiricism will actually compound and lead to the uncertainties that I showed you before. And the reason is because clouds are really crucial, right? They can reflect energy back to space, so they can cool up the planet. So you need to do a very, very good job at representing those clouds in particular. They are really crucial for the fate of the planet. But it's not just clouds. You also have things that are very important in the ocean, such as ocean eddies and turbulence in the ocean that can actually store then energy in the ocean and also help mitigate some of the warming that we have in the planet. And as I mentioned before, you also have the biogeochemical cycle, so the carbon cycle, which is very important. And for that, it's also much more complicated. If you just look at a single tree, you have many, many different leaves and even stomata at a smaller scale. So we need to represent all of that complexity in a very coarse scale model. And of course, we need to be extremely empirical in the way we are doing that. And that leads to a lot of the uncertainties that we have there. So basically, at the end of the day, we have many of those uncertainties that are compounded together, leading to the uncertainties I showed you before. And we really need to nail that down so we can have more actionable type climate information for climate adaptation. And that's kind of what we are hoping to do as part of it. So what are the solutions to get there, right? So I mentioned that we have many processes you cannot resolve. So you could say the obvious thing would be like for turbulence, you just resolve more. Like give me more compute, and if I have more compute, I can resolve more, right? And this is one way to represent that. Those are different scales of interest, and this is the length, the time scale over which we want to resolve that. For climate, we typically want to look at hundreds of years, right? That's the typical time frame we have. That's typically what we use for policy making and for infrastructure planning. And we need to resolve the entire planet, so thousands and thousands of kilometers in scale, right? So that's kind of the area we need to cover. But we are very much limited by the compute. So if you look at a typical climate model now, we are again at a resolution of roughly hundreds of kilometers. And we can only run that for like relatively coarse time step, and then we run that over hundreds of years because that's what we are hoping to resolve. But what it means is that for anything that's below this scale, we actually need to represent that again empirically. We call that a parameterization, right? We need to have this empirical way of representing the world at scales that's smaller than what we could resolve. You could go down that route here, and you could say we can go at higher resolution, but again, the compute will be higher, so we can potentially run that at a kilometer scale. We call that a cloud resolving model. We're going to see a few of them later. And then you're resolving clouds better, but you cannot really run them for a very long time because the compute is just out of its scale, right? So that would be not feasible, at least in the next coming decades. You could go to even finer resolution. That's where you're actually resolving clouds a lot more. You could really resolve like the puffy aspect of clouds, and that's actually very important. But that's even more computationally expensive. So you can only run that over, like, say, 100 kilometers in scale, but not more than that, right? And then you could go all the way to the end. So that's what people use in turbulence with what we call direct numerical simulations, where you resolve all of the turbulence. But that's only over a box of roughly a cubic meter, right? So that's very, very abstract and very empirical, you could say. And so the obvious thing is just give me more compute, right? I'm going to scale up my problem, and I'm going to be resolving more and more things. And I know that I'm going to be doing a much better job at resolving clouds, turbulence, and all of the processes that actually matter. But as I mentioned, we are very much limited by the compute. We are trying to put that on GPUs, but even then, we have strong limits in terms of the scaling we can have. And that's basically out of the question, or at least to run serious climate simulations. Another approach you could have, and that's what we've been trying to do as part of LEAP, is going the other way around, where what you can do is you can learn from those higher resolution simulations that are doing a good job at representing clouds or turbulence, and then scaling that up, right, using machine learning potentially or some statistical technique, but it could be also physically based. So that's going basically up the ladder here. And I'd like to emphasize that they are not disconnected. You can actually do both at the same time, right? So the more compute you have, the better, because you can resolve more. And you could still use some AI at the end or in tandem as well. So they can actually work in parallel. But that's true for turbulence and the atmosphere and the ocean, but you also have many processes that you cannot resolve just with more compute. One big example is actually clouds, and thinking about what we call microphysics, so how you create clouds and cloud droplets, cloud crystals. And that's a place where we basically barely know the physics, right? So the compute will really not buy us anything here. Another example here is just looking at the terrestrial ecosystems, right? There's such a diversity. This is just an example here. You could have an urban area here, which is extremely complex, like buildings, trees, and humans, et cetera, et cetera. And for that, I mean, there's just no hope with compute, right? I mean, you need to have some sort of empirical representation of that. And again, machine learning and artificial intelligence could be a way to kind of mimic the real life and mimic the real world at a fraction of the cost. And for that, we cannot really simulate things. I mean, we can use that and then run simulations, but we cannot really simulate the landscape that well. So what we will need to use is still observations, right? They could be from lab studies in situ, or they could be coming from satellite observations. And we'll use that to learn and better represent the processes that we have. But these days, we have the advantage that we are really witnessing a data revolution, especially in the earth science, right? We have many constellations of satellites that are actually rotating around the Earth every single day. We are observing photosynthesis. We are observing the amount of moisture in the soil. We are observing many different factors that are affecting the Earth and the climate. We can also launch and run many detailed simulations over a short period of time, but I mentioned some of those. This is here a cloud resolving simulation at the global scale. And you can see we can resolve many of the small details of clouds and how they are puffy and changing every day. So that's something we can actually learn from. And of course, here we're talking about petabytes and petabytes of data, and you need to actually be learning from those data at scale, right, and from those data sets. And then the only way to get around that is to use AI, and it goes without saying that we've been witnessing this transformation from AI and to really leverage the data revolution as well. So we can really extract meaningful information from those data sets at scale using AI. So I'll show you very quickly some success that we've been having, for instance, using AI, especially for climate modeling and where we are actually seeing some impact. And then I'll try to talk about some of the challenges. So this is an example here again about those super detailed cloud resolving simulations. So this is a global simulation of the Earth and the atmosphere and the ocean at roughly a kilometer scale. And you can see we can resolve again clouds and what we call convection, so clouds that are precipitating, so typical summertime clouds that are very important for climate. And we can resolve them relatively well, especially in the tropics where they are actually very important. And what we can do in that case is because we have this fine-scale simulation, we can use what we call supervised learning, so very simple strategy, and we can just coarse-grain that at a scale that's similar to a climate model. So we go from kilometer scale, we coarse-grain that to 100 kilometer, which is equivalent to the climate model, and then it's just a training a task where you have your supervised regression, and you just want to regress against some data that you have. So that's pretty straightforward. And we've done that. So at the time, that was almost prehistorical by now, 2018, where we actually did that. So at that coarse resolution data, we tried to train this neural network to reproduce convection and reproduce clouds, which is basically what you're seeing here. You have the coarse models, so the coarse resolution state, climate model state, so temperature, humidity, wind. Plug that into a big neural network, deep learning, and then we are trying to predict the next time step of that model, which is based and which very much depends on that convection and the clouds. And what we could show is that we can even plug that neural network back into the host climate model. So we just replace the historical or the traditional way we were doing clouds and convection. We just replace that by a neural network. And what we could show is that this is the reference high-resolution model here, and this is the coarse resolution model in which we've plugged the neural network, and this is just the bias here compared to that. And you can see that the bias is close to zero pretty much everywhere. This is across latitudes, this is a long-term average. But you can see that even when we couple that into the host model, we are doing a great job at representing temperature. So there's hope in terms of trying to really reduce that uncertainty that I showed you before in terms of temperature by representing those physical processes better. And we can use, in that case, potentially high-resolution simulations and learning from those. On the right-hand side here, you have the standard historical coarse resolution, physically based climate model. And you can see you have major biases here, for instance, of many degrees in the tropics. So that's a well-known bias that we have this typical double ITCZ intertropical convergence. So that's a well-known bias, which is highly problematic. Also to think about precipitation in the tropics and the impact it could have on life there. So we were pretty hopeful when we saw that. You can also look at that in terms of space. So this is here showing you this high-resolution simulation at the top. and for two different things. So on the left-hand side, you're seeing the amount of moisture in the column, and on the right-hand side, you're seeing precipitation in log scale. And you can see that the neural network can very, very accurately reproduce what we are getting from the high-resolution simulation, right? So this is very hopeful. It means that AI can really do a good job at representing complex processes, and precipitation in particular is very complex, right? You can have a lot of extremes, as I mentioned before. It's a lot of on and off. A lot of times you don't have precip, but a lot of times you have a lot of precip, right? So it's a complex process to represent, and AI and machine learning can do a great job at representing that. And it's very skillful, you could say. So that was very helpful. And then we could show that the typical bias I showed you before, the fact that typical climate models tend to what we call drizzle too much. They don't have really intense precipitation that are so impactful for adaptation, which is shown here again in green. You can show that when you plug this neural network back into a climate model, you're much closer to the truth here, which is in blue. We can finally pick up those extremes by embedding this machine learning into climate models. So that's very hopeful again. It's not just for the mean temperature, but even for extremes, all of the variability, we could also show that we can get better variability of climate. This is showing you that climate and the way we represent those processes can be really crucial in the way we can do those things. Another thing and typical bias that we have in climate models is thinking about the Darno cycle. So it sounds ridiculous, but climate models don't rain at the right time. They don't rain when they should be raining. And this is an example here where this is the standard climate model, like one of the reference climate model over the US. And the typical rainfall, the peak will be early afternoon, which is a very typical bias that models have. And instead, if you look at observations, and you will see that the model is actually like here in green, you could see that the peak will actually be earlier, and you have a second peak potentially at night. And now if we plug again this neural network back into the host model, we can actually get those two peaks. It's not perfect, but we are actually much closer from the original climate model. And of course, that's information that's going to be important, even for plants. That's the amount of light that they are going to receive and the amount of carbon that they will be able to uptake, but also for even impact. You can see that they are very, very different types of rainfall. So those are great news. It means that we can do a good job there. There's also some great work, for instance, on the ocean. So this is work by my colleague Lorzana at NYU, where they could also show that by using machine learning, they could very much remove many of the biases that we have in the ocean. So if you're interested, happy to talk about that, but I'll just move very quickly around that. But it's not just for the atmosphere. The other thing I wanted to mention is that it's not just neural networks, but we have some other tools in the artillery. One thing that's pretty exciting to me is also to use symbolic regression. And what we mean by that is discovering equations based on data. And what you do is you have a very large data set and very large database, and what you expose that to equations, and then you're learning an equation. So this is here the equation that we learn for cloud cover. So how you make clouds based on temperature and moisture. And this is exciting because when you see the equation, most people can actually interpret, or scientists can actually interpret those equations. It's pretty obvious, as opposed to a big, deep neural network, which is pretty much like a black box, right? So it builds a bit more trustworthiness, which is sometimes important, especially in the climate community. People want to know why they are making a particular decision. And just to give you an example here, this is the original core scale model here. At the bottom are the observations. And this is this is a high resolution product. You can see that there's a bias even then. Those are the observations here on the right-hand side. And when we use this symbolic regression, you can see that we are actually very close to the observation. So we can do a great job, even with something relatively simple that we can grasp and we can directly understand. So it's just to emphasize that it's not just deep learning, but there are some other tools in the artillery that we have. Some of them are pretty exciting, such as this symbolic regression. But I'd like to emphasize that, so we've made progress, but in my perspective, it's been too slow. And especially if we compare that to the weather community. So a while back, actually, one of the co-authors that we had back in the first paper that we had on the use of deep learning for climate, Stefan Rasp, he was a visiting student from Germany. In parallel, he started this benchmark data set for weather. And what they did is he created this weather bench that really started a little bit under the hood, pretty much unnoticed at the time. But it got a lot of people really interested, especially in the AI community, because that was a very well-defined data set with very clear benchmark of success. And they could try to actually run some pretty sophisticated architecture to try and reproduce weather and beat typical weather forecasting centers that are typically physically based. And you can see the progress here, like 100% will be the skill of the reference model, which is the European Center, Center for Medium Weather Forecast, which is very well regarded, which is viewed as the reference in the world. And that's the baseline of 100%. And you can see this very rapid progress where in 2018, when people started using at the time some convolutional neural network and UNet, that's the type of skill that they had. They had less than 25% of the skill of this physically based model. And very rapidly and very abruptly, you could see the increase in the skill, and not just in the skill, but also in the resolution that they are actually resolving. Now they can actually resolve those forecasts with great details and great accuracy as well. And you can see kind of in 2023, there was a breakthrough where many groups, including DeepMind, Google, I'll show you some results as well, Fuji, Panji Weather, and many other folks, NVIDIA as well, have been beating this reference model. So this is exciting, and that's where the field is going. It's a paradigm change. The way you're getting your weather forecast now is based on physics-based model, and that's going to change, right? That's starting to be AI-based. In Europe now, they are integrating this AI-based forecast, and that's a paradigm change that we hope will get in climate as well. So that's been really a game changer. And again, a lot of that started because of that benchmark, and we'll get back to this in a minute. So benchmarking and data sets are crucial for progress, and we should make that a community effort. And just to show you one of those examples, so this is GraphCast here. So the model by DeepMind, so they are a company now bought by Google. They are based in London. A lot of innovation that they've done, including protein folding. And they do a great job in terms of predicting, but at coarser resolution than the benchmark, if you will. You can think of that as observations. But they can pretty accurately reproduce the observations. And that was, again, the breakthrough that we mentioned before. One thing I'd like to mention is that if you look at those, they tend to be blurry. And we'll get back to this later, right? We'd like to have the fine details, right? Because they can be important. Like, for instance, a tropical cyclone will be about the details of the wind or rainfall. And we need, especially, for instance, today in Florida and yesterday, that's what you want to get exactly right? Because that's important for impact. I'd like to mention, and if you're interested, happy to talk about that, but it's not just an issue with machine learning models. Some students in the group have been showing that even with machine learning, you can do a great job and you can be very, very crystal clear. But those are some of the challenges, and we'd like to actually be at the same pace, right, as the weather revolution, right? So it's been going very, very quickly. So there are some challenges on the way. Some of the challenges that we've been witnessing is that, for instance, for climate, it's a little bit more complex than weather, because we're not just trying to replicate things that we've seen many times. We're trying to generalize things that we've seen very few times, right, or very rarely. For instance, an extreme drought, an extreme flooding event. Those are very rare events. By definition, a 100-year event comes every 100 years, except with climate change, it's actually more rapid now. But that's something that you didn't have very much in your record, right? So using just machine learning and AI is challenging there. We also have some numerical instability, so if you're interested, we could get into that. But many of those schemes, when you actually try to use AI, eventually they blow up and you get temperature of the sun for the Earth, which is not what you would want. And that's not related to climate change in that case. It's just a numerical bug. You also have a lack of physics, and typically you would want to embed some sort of physics. There are physical laws, like we know gravity, of course, but there are some other laws, like Coriolis effect. You would want to embed some of that in your physics so that it can generalize relatively well across. So that's called equivariance, and there are some really interesting work around those lines. But some of the biggest gap, I would say, is actually very simple. Is that when we develop a climate model, we actually use very old programming language. We use Fortran, which was really much more prominent back in the 80s and 90s. But now, I don't know how many students here actually know Fortran. I would guess very, very few of them. Great. But most people know Python, right? And so that's a huge roadblock for the community because we need to make those codes more inclusive, and we'll get back to this later. And I'd like to mention just very quickly that the generalization, there are ways around that, right? So we can potentially merge things where what we can do. So this is a strategy that we've used where we could what we call a multi-fidelity type of approach, where what you can use is you can use physics as a first guess, and then you can correct that with machine learning, right? So you could have two guesses. You could think of that physics gives you the prior, and then that would be your low fidelity, which is not perfect, and then you just correct that, you tweak that a little bit with AI. And that's a way we showed that when you compare that to, say, so when you're trying to predict the future. This is the higher the color, the stronger the color, the better. This multi-fidelity can predict the future really well. This is a warming experiment where we know the truth. We had a high resolution truth. And the higher you get, the better. And we can show that this multi-fidelity can beat any type. So it can beat a physics-based model, which is this low-fidelity model here. And it can beat also a neural network that was just trained on the past. So basically what I showed you before. So it means that putting some physics can help, right? So some physics can actually help extrapolate to a different regime. And there are different strategies to do that. So the multi-fidelity is one. You can also do some sort of physical invariance. So that's something we've been doing as well, where you can find numbers and variables that don't change with climate change, right? So that's another way to do that. So if you're interested, happy to talk about that, and the reference are here. But the real question is, where do we go from there, right? So where do we go, and how do we get at the pace of the weather forecasting, and especially AI-based weather forecasting system, right? So we are making progress, but it's too slow, and we have a lot of constraints in the way we are actually doing those things. So we'd like to actually move faster. So I'll try to first look back and step back for a minute and thinking about what were some of the lessons that we learned, and what were the drivers of the AI revolution. And oftentimes we forget about those. We just think about GPUs and things, but we'll get into what are some of the pillars. And people might have different views. This is my perspective. So there's definitely a biased view of that. But I would say, for me, there are at least 5 pillars, right? The first one is modern algorithms, right? We've been able to do relatively sophisticated things, right? Backpropagation is one, so how we compute gradients, how we estimate and we optimize a lot of very complex functions. So that's one. Massive amount of data is obvious, right? So now there's a competition for data. Like when we think about OpenAI, they're always looking for more, like now using YouTube videos and trying to get the caption as well. So you need more data. The more data you have, the better your algorithm. You need modern compute as well. Being able to actually parallelize that at scale, that was a very important part of the AI revolution as well. And I mentioned that to you before, benchmark data sets. I would say that was one of the first things for the AI revolution. We created some benchmark data sets so that we knew what success was, right? We knew what it was to do better. And maybe one thing we don't think so much about is high-level programming. It's so easy these days to actually do deep learning. You get into a class, the next day people can start building on your network. That was not the case 10 years ago, right? You had to do it potentially in C++, coding that yourself, so that was a lot more complicated than what it is now. So that's been under the hood. That's, I think, a huge factor that has led to this AI revolution. It's very inclusive, very fast, right? And the life cycle is really accelerated. And when we think about modern algorithm under the hood, so sorry to get a little bit into the weeds, but we'll get back to this later, is what we call differentiability, right? The fact that we can take gradients to function in a very efficient way. And why is that important is because typically we want to minimize some loss function, right? So we have a mismatch, say, to some observation or some data set, and we want to actually replicate that as best as we can. So this is the loss function. That depends on a bunch of weights. Those are the knobs that we're tweaking in the neural network. And what we do is we just use chains rule, right? So that we can actually minimize this loss by backpropagating that through the neural network. And for that, what we need is we need to compute the gradients, right? The gradient of the loss to the output here, the output to the function just before, the network, the neuron just before, and of the neuron to the weight just before. And for that, what's very efficient is to use differentiable automatic differentiation, right? You can take the gradients basically for pretty much free, and that's a huge leverage, right? Because you can have complex functions, and now you can take those gradients, and you can compute that very efficiently, and that really scale up your algorithm. That can really very, very efficiently accelerate your algorithm. So that's actually really fundamental in the way, in the acceleration of AI. The second thing is parallelization, right? The fact that, for instance, now we are using a lot of transformers as opposed to at the time we were using what we call long short-term memory systems, so to look at sequence. And a lot of that was based on this attention mechanism, and the big leverage could be that now we could parallelize things instead of storing the entire sequence and sentence or even paragraph or book, right? Now we can actually parallelize that, and we can use many, many GPUs. And that's also why now GPUs are also such a golden asset, because they are so important for those things. And this is just showing you an example with transformers. The accuracy is just through the roof very quickly compared to standard LSTM, right? So that's been a revolution. We can really scale up and do that at scale. The second thing has been data, especially for AI. One of the earlier revolution was this so-called ImageNet, where people had pictures of cats and dogs and bananas, and they were labeled, right? And that was a great way to start training and getting success, right? You would know what was the accuracy of your model. And that's been really the leverage of the AI revolution. And as we mentioned before, now the more data you have, you can even go to YouTube. That it could be videos, not just images. It could be all sorts of things, what we call multimodal, like all sorts of different types of data. And that's what you want, right? The more data you have, the better the algorithm. And along with that is the GPU revolution, right? The fact that now we have those very greedy algorithms that really need to be scaled up and that need to be parallelized. And that's been explaining a lot of the success of a historically video game company or doing cards for video games. And one of my good friends, actually with whom we started this thing, now he's at NVIDIA and started actually a little bit before that bump, so he's pretty happy about it. So he buys me some drinks, I have to say, from time to time. And then we also need to have benchmark data sets, right? We need to have very clear benchmarks for success, right? We need to know what is good, like what does it mean to be better? And that's a big thing, right? When you want to have like domain scientists talking to machine learning scientists, right? You need to let them know this is what we call success, right? Because that can be relatively abstract and relatively subjective, right? And I mentioned that, so ImageNet was a huge revolution for computer vision. And this weather bench that this former student, Stefan Rasp, actually put together has been at the heart of that revolution for weather, right? People are always going back to that benchmark, and they know what success is, and they can spin up and increase the complexity of their algorithm to do a better job. So that's actually crucial. And benchmark here means a good well-organized data set along with a metric of success. That's what a benchmark data set is. And finally, again, that's what I mentioned before, is that we need to have codes that are easy to change, right? You want to have a cycle for iteration that's really fast. And when we think about that, I just put that here. You're building a relatively sophisticated architecture, and that's what it takes now. This is not super complex, but you need to have spatial and temporal architecture. This is a convolutional neural network stacked with an LSTM, so you have time and space, relatively sophisticated architecture, you could say, or like when you're starting in machine learning. And those are the only lines of codes that you need, right? It's very little. A few years back, you would have like thousands and thousands of lines of codes, right? So it's actually a lot easier than what we had before. And to train and save the model is only that, right? Just one line and one line, right? So this is really inclusive, right? And it means that we can share codes, we can share development. So that's a huge leverage. And a lot of that is based on Python. So at a high level, you have Python, but then the optimization is done under the hood, and you don't see that, right? You're leveraging a lot of GPUs, but that's really transparent to you, and that's really agile. You can do it on CPUs, you can use it on different GPUs. So there's this agility, which is great, yeah, and very, very far from what we have in climate models. And also a lot more inclusive for students in particular. So can we learn from that and use some of that for climate models, but not just only climate models, I would say for computational science, like physical science in particular, and leveraging some of that. And at the core, I would say, is also differentiable computing. Like I'm going to show you some examples of that. And really what we want is actually leveraging some of those things, right? We want modern code and compute, right? We want to be able to kind of code in Python because it's easy and pretty easy to iterate on. We can actually plot things. But at the same time, you want to actually have fast compute, right? We know that the compute is really important. We want to have many, many GPUs. And we have tools right now where we can actually do that at scale. So I'm a big fan of JAX, but there are some other tools such as PyTorch, where what you can do is you code in Python, but then under the hood, you have a lot of high-end optimization being done. And this is just an example showing you a great example here where they took an ocean model that was based on Fortran. They converted that in Python JAX, and they could be at almost the same performance. So NPI is on what we call CPU, so standard type computing, and they could be at almost the same performance. But then the advantage is that they were never able to actually run that model on GPUs, and in just one line of code, they could actually run that on GPU. So that's a huge leverage, right? Just recoding that in JAX, and then they could run that. So, and they didn't do a great job. They told me they did it over the summer, and that was it. So that's great. The other thing is once you're actually talking in a language that looks like AI, then it's easy to integrate AI, right? So it's pretty obvious. So meaning that you can really be hybrid, right? You can have some parts that are physically based, you can have some parts that are AI based, you can integrate those things. And you can think of that as Legos, right? Those are building blocks, and just think of that as Legos, and they can be intertwined and they can communicate, which we cannot do right now. And they can actually do that bidirectionally, and we cannot do that now. It's also much easier to harness observation, right? We can actually use AI, we can actually use a lot of preprocessing on the data which we are using, and then it's much easier to actually assimilate data and many of the observations that we had before, which is kind of at the end of the process for climate modeling, because it's so complex and it's very difficult to tweak those models because they are based on Fortran. We don't know how to optimize those, so it's a lot more seamless to actually do it this way. And finally, for some of those pillars, we also need to know that we are doing better. So we need to actually also define benchmark data sets. So those are, I think, some of the pillars that we need for like a new type or new generation of physically based computational science. So I show you a couple of successful examples in my perspective of some of those things, and they are starting to actually get into the physical science. The first one is that example I showed you before, this ocean model that I showed you earlier. And what they did is they, again, over the summer, they just converted that to Python JAX, and then all of a sudden they could run it on GPUs. It was much easier to run. And again, that's the performance that you have. So you're a lot more efficient than what you have what you could do before. Also, in terms of emissions, like carbon emissions, GPUs are a lot less emitting than CPUs. So this is also a lot more efficient from a computing perspective. So that's great. And they could leverage, for instance, 16 NVIDIA A100, so pretty good GPUs. And they could run the model at a resolution that they could never achieve before, like very, very fine scale resolving turbulence and things. Just by converting that for something which sounds absurd, converting that to Python, you would think it's the wrong thing to do because it's less optimal. But no, if you can actually then leverage a lot of those tools coming from the AI revolution that are under the hood for you, then you can actually leverage those. And I like to emphasize that this is great because once they have that, so it's simple to write. I mean, this is actually from Dion himself. It's easy to scale up because you have all of those functions, and you can run on any hardware. This is how it's running on CPUs, this is how it's running on multiple CPUs, and this is how it's running on GPUs. Just one line of code. You're changing one line of code. No need to rewrite that with CUDA and all of that stuff. So this is great. There are some other examples here, for instance, from folks at MIT, colleagues there, where they've done kind of another strategy, starting from scratch and rewriting everything in a slightly different language, which is called Julia, which is used by some folks in the physical science, where you can also use some of those tools. But just to mention that it's not the only example. But what's great is that once you have those tools, you can also use a lot of the deep learning tools. So this is also used a lot now in turbulence. So this is some great example for fluids and turbulence. And now you have this JAX solver, so you can write it in Python, but you can also influx as much as you want some machine learning component. And I just wanted to highlight what's written here. Written entirely in JAX, it's straightforward to include existing machine learning models in the framework. And we can do end-to-end optimization. And that's exactly what we want, right? We want to have parts of the physics from time to time. We might change that based on our needs. And from time to time, we want to have machine learning. And we want that to be very flexible and very agile. And we want to be able to run that on GPUs, right? And that's basically what they are doing here. Great. And then in the background, what we want is, I'll get to that just very quickly. Again, another set of equations is to think about what we call automatic differentiation. And what we mean by that, so if you just remember a little bit of your calculus in high school, or maybe it could be undergrad for some of you, imaginary number, you remember it's I squared equals -1. And you can do the same thing with this epsilon here, which is epsilon squared equals 0. And that's a great trick because what you can do then is you take a function here, and you do a Taylor expansion, right? X plus a little epsilon here, that's going to be f of x, plus epsilon times the gradient, plus the higher order terms. And what you do is you say epsilon squared equals 0. Same thought experiment as well, thought process as what we did for I squared equals -1, right? And now what it means that every time you see epsilon squared, you drop it to 0. And it means that now you get access to the gradient for free, pretty much, right? So if you could run it pretty much twice, you could get your gradients for free. And that's great. So, and that's very much at the backbone of a lot of those tools I showed you before. PyTorch or JAX that we are using that. You have a function and you can take the gradient pretty much for free at numerical precision. So that's really, really great. And you can think about optimization problems and tweaking those algorithms pretty much the same way we've done that, as I mentioned before, for machine learning and AI. It's the same process, right? The exact same thing. And once you have that, you can do all sorts of things. You can do parameter calibration. You can do uncertainty quantification that people like to do when they have noisy observations. And you can really build this kind of hybrid model because you can take the gradients of the physics or the gradient of the machine learning component. They are the same thing, right? Those are just Legos, and the backbone is the same, right? So just play with your Legos. Everyone likes Legos. Such an example here is actually from Google. So this is work from Stefan Hoyer's group at Google Research. And what they've done is that they've created basically an atmospheric model, which is like, you could think of that, it's a weather forecasting model, which is based on JAX. So again, this Python code, which is differentiable and also can be leveraged on GPUs. And as he mentioned here as well, this is his slide. It could also be on PyTorch and Julia as well. But the big advantage is that you have a physics-based dynamical core, so which is moving things around. And then you have a big neural network, which is taking care of all the physics I told you is complicated. Clouds, convection, turbulence, gravity waves, all of those things we don't know. That's taken care of by the neural network. But how we move fluid around, we kind of know the equation. So why would you want to emulate that? We can do a great job. And then they predict the next time step, and they do it many, many, many times. That's what they do during training to make sure things are very stable. And when they do that, so that was published this year in Nature, they can actually basically plug this whole thing. So that's what they call the neural GCM, neural general circulation model. So that's a climate model based on a big neural network coupled to a physics-based solver. So you have the physics-based solver, which is here, coupled to a neural network. And again, they are like Legos, right? They are different things, but they are all differentiable, so they can communicate and you can tune them together, which is great. Okay, so that's pretty unique example where you already have those two pieces, the physics and the machine learning can communicate in that particular example. And what they could show is that it can solve the issues that we had before. If you remember in the first video I showed you, it was blurry on the right-hand side. But now if you add the physics, you can see that it's actually not blurry. They can do a great job and they can get all of the fine-scale structure that you didn't have before. So it's really telling you that by bridging between physics and machine learning, you can potentially get what we wanted, right? We can get accurate prediction and we can get some of the crispness that we wanted to have in the first place. So this is a great example, I think. Here at Columbia, just very quickly, we've been doing a similar type of approach. So this is great work by a student, Jianing Fang, where we've been trying to do the same for the carbon cycle over land. And what we are trying to do is estimating the carbon pool. So you could think of that, how much carbon is there above ground, below ground as well. And we are using satellite data in that case that we are assimilating to actually produce those pools. And you can think of that so that we can estimate carbon uptake over land. And we are looking, for instance, at the impact of El Nino on carbon uptake or the impact of climate change. So you can really use that to estimate in almost real time the carbon uptake from the land. And the advantage is you can plug whatever function you have. So if there are things you don't know, some of the physics you don't know, you can actually replace that by a big neural network. This is an example where we don't typically know how plants respond to water stress, so we can actually learn that function. Okay, so without getting into the weeds, we plug that neural network, we expose that to data, satellite data, and you can learn that, and you can learn that end to end. So that's great. You have a neural network embedded with some physics, and that's actually representing things that you don't really know how to represent really well. And you can also predict across space, so just I'll spare you the details. But this is an example here where what you can show is we can predict biomass relatively well, so that's across space. This is total above ground biomass. We are doing a good job there. And also the amount, because it's not just carbon, we also have water. We can look at the amount of water below ground, and you can do also a good job across regions of the globe. So this is pretty exciting because just by ingesting data from satellite, we can do a great job at actually predicting in other regions of the globe. Those are in the test data we've never seen, and we can do a great job. And that can be potentially used later for informing in terms of carbon uptake, but also policy making, thinking about, for instance, land use, land cover change, and reforestation, deforestation. What is the impact on carbon pools and carbon fluxes? I'll skip that. But that's kind of the vision at the end, is that what you'd like to basically bring everything into a hybrid mode where you can actually learn from high-resolution simulations, from observations. You merge all of that into a big neural network, you could say, And potentially you can even use generative AI to generate many, many ensemble members because you'd like to generate some variability. It can be variable from year to year, so you can actually generate many ensemble members. And then potentially even downscale with machine learning as well, so you can drive your impact model and you can have accurate physical risk and towards climate adaptation. So that's a paper that was just published on Wednesday that we got where we really showed this vision about really embedding that into an end-to-end framework where we're really bridging between physics and machine learning with this type of hybrid type of approach. And my view of the world, so that's kind of the schematic, is really Legoland, where you can just plug and play, right? And that's what we all really like Legos, right? So we like to actually plug and play, and we like to replace sometimes by some machine learning, some components, maybe the entire component, depending on the needs, depending on the time scale, depending on the question we have. And that's really the goal, right? We want to have something really agile and really flexible. And that was, of course, generated with ChatGPT. And of course, as I mentioned, you need to have, just to wrap up, you need to have benchmark data sets, right? So you need to actually know that we are doing better. So this is an example of a data set we put together as part of LEAP. This is called ClimSim. So that's a data set where we are using that for basically an entry point for climate science and trying to replicate some of those high resolution simulations. And that's a data set that's available online. And we have metrics of success, so if you're interested, you can directly play with that. I'd like to emphasize that we will have a new hackathon. So this is for sub-seasonal to seasonal forecast, where we are going to be using that. So that's going to be on from November 13 to November 15 with AWS and NVIDIA. Again, a great data set and benchmark where we like you to do better with machine learning. So if you're interested, please reach out. There's a website going on, so you can register if you're interested. Okay, so just to wrap up, I would say we can also now think about generative AI, right? So there's going to be a key role that generative AI is going to be playing in the future. And generative AI can come in for many different aspects, right? So it can represent uncertainties. It's a nice probabilistic framework. If you don't know diffusion models, that's what is used for DALL-E, for instance, right? You have a prompt, you generate an image, and you can think of that. That's a great way to generate things, right? And our climate problem is not very different, right? We are at a coarse resolution I mentioned before, but we like to be crisp and at a fine scale resolution. So you could think of that as just a prompt, right? We know the coarse scale, and we want to do the fine scale, right? So very similar type problem. And so you can use generative AI to do a lot of those things, and diffusion models to bring in observations. So that's what we call data assimilation. Some great work by Yongchen Xu and Juan Nathaniel. They are in the room if you're interested. We can use that. So those are from colleagues at NVIDIA to downscale and define fine resolution results. This is for a tropical cyclone. You have the coarse resolution result here, the fine resolution wind, precipitation, things that you need to look at the impact of a particular storm, right? And you can use diffusion models so they can actually go back and forth between the coarse resolution and the fine resolution. So you can go all the way to the impact with the diffusion model, right? So there's a lot that they can do. You can also use them for simulation. So again, that's similar to what I showed you before. You have the ground truth here for turbulence simulation. And you have, for instance, the coarse estimate based on machine learning. And you can see, again, you have this kind of blurry simulation. If you now add a diffusion model onto that, again, like this prompting like DALL-E, now you can see we can actually generate all of the fine scale structure, right? Which is great. And you can see that even the physics is great. This is what we typically look at in turbulence. Those are the spectra. And you can see the turbulence are spot on. Somehow the diffusion has learned physics. It has learned some aspects of turbulence at the fine scale. So this is really great. This is another way to look at that. This is the coarse scale estimate of that. You correct that with the diffusion model, and you can see you're almost spot on. So this is great. So diffusion models can learn fine scale physics. So there's something to be learned from that. Yeah, I'll pass that very quickly. So we can also use large language models for trying to translate. And I mentioned that one of the issues is the fact that we're in Fortran, and we can also use large language models and generative AI to also translate some of the code. So those are things we are doing with some students here to get into Python and to get into JAX so that those codes will be more inclusive. So that if you're interested, please reach out. That's a big effort we are trying to do so that we are not just stuck in Fortran. So to conclude very quickly, so I think we can learn for the physical science and computational science, we can learn from the AI revolution, right? And especially in terms of their pillars, right? The fact that we have a massive amount of data, we need to have modern algorithms that are differentiable and parallelizable as well. We need to be really agile to different hardware, from CPUs to GPUs. People have different configurations, and we need to be able to run on many different types of hardware. We need to be coding at a very high level, right? So I would say Python is going to be the de facto way of doing that. And under the hood, you can do all of the parallelization, right? That would be the right approach. And finally, the underestimated thing is, again, benchmark data sets, right? We need to know what it means to be better, and we need to provide data sets for the community to actually do a better job. So that's actually very crucial. And there's going to be a lot coming from generative AI, so I'm very excited myself by diffusion models, but they are going to help to improve simulation, again, representing some of the physics we don't know. They are great for that. Also assimilating data, merging data and models, so they can actually do that as well. They are great assimilator, as we call them. And to actually do what we call downscaling, also refining the resolution, prompting, right? You're prompting you at a coarse scale, and you want to do that at a fine scale. And in the meantime, they can also help us potentially transfer those codes that were in Fortran into Python and a more modern way of doing things, so that we can be more inclusive and include a broader community, so that we can accelerate faster. So with that, I'll be happy to take any questions. Thank you.
I'm from the Blockchain and Climate Institute. It seems like a lot of the AI, it's great, it's what it can do and improving the models. However, this is all to respond to the issues related to the climate change and the excessive carbon in our atmosphere.
Yes.
Is there any, have they rolled it out to do anything to address the carbonation in our atmosphere, or anything to help reduce the carbon in the atmosphere?
Yeah, that's a great point. So they are great, actually including at Columbia as well. People are thinking about material, and you can use generative AI to improve materials to actually do carbon capture and sequestration. So those are great areas. If I were a student, I would potentially go there. That sounds like a really exciting area, but you can use generative AI to think very much like what people have done, like to think about new proteins and things like that, or drug discovery. So it's material discovery. This is a very, very exciting field, in my opinion.
Hi, my name's Sophie. I'm a student here at Columbia. So I had a question. How do you reconcile the fact that using machine learning to make climate models with the goal of, perpetuating the longevity of the planet is also affecting the planet through carbon emissions due to the amount of energy running the models needs? Like, do the models account for this? Can they?
Yes. So I would say, especially in Europe, they are very careful about that. So when they have a new version of the model, they very much compute the amount of CO2 emissions that are related to model runs and simulations. There's a huge advantage of using AI for that, because once you've trained them, which might take some compute, they are really cheap. And that's a huge advantage compared to physically based simulations. So I see that as a huge advantage, especially when you want to think about extreme events where you need to run the model many, many times, because a 100-year event by definition is every 100 years, so you need to run the model many, many times to build statistics, right? And that's computationally very expensive. So I think there's a lot that can be learned from that. Also from the fact that most of those models are not on GPUs. They are on all CPUs, which are a lot more greedy in terms of CO2 emissions. So that's also one place where that's a huge advantage to move to GPUs and to move to this type of architecture. Yeah, that's a great question.
We'll have one last question. Or maybe two.
Yes. Okay.
Yeah, go ahead.
Thank you. Thanks for the very good presentation. I was wondering if you have any examples of policy application of your science, or like your results of your models.
Yes, so we're actually working on that to think about. So at this stage, we are thinking about subcontinents as agents. To try to think about mitigation and how can you actually mitigate carbon emissions, because we did that a few years back with a student, but we just looked at the global impact, but now we are looking at individual agents and how they can interact, how they can trade, and how they can potentially, you can try to optimize the trajectory for mitigation with different agents. It's a bit different from that, but it's kind of using also generative AI at the core. So it can inform policy making potentially.
Yeah.
Thank you so much. I'm sorry, I came a little late, so you might have answered this already, but I was really curious. I work internationally over 130 countries, and I think this is a wonderful time to really get collaborative very fast, right, from around the world, Europe, Asia, wherever the talent and models might have been built. So I'm curious to understand from your point, where are some of the 3 or 4 cutting-edge places that is already got applied research in action that folks, so the wonderful students here and elsewhere in the United States and other places can collaborate, and if there are any programs that actually work in that capacity already. Thank you.
Yeah, that's a great question. So I didn't really have time early on, but I mentioned that we are building this cloud-based data platform, right? And we are collaborating with a few partner organization on profit so that we can actually scale that up, so especially towards the global south, so that people can get access to climate data at scale. The next step that we are thinking about is thinking about compute, right? So that people could actually run the compute on the cloud. They don't need to have resources in a particular country, but they could actually leverage some of that there. So those are, I think, the 2 pieces: getting the data to the world at scale, so to anyone, anywhere. That's my hope. Climate data, and potentially in a way, in a format that's easily accessible to various people, and then making sure that they can get access to the computer, that they can refine the answer for their particular needs. For instance, you're in Kenya, you would want to know what is going to be the impact in Nairobi of that particular thing. You could actually run that yourself. And again, if those codes are in Python, it's a lot easier to do than Fortran.
We'd like to thank Pierre for the wonderful talk.
Yes.